Okay, well, good afternoon, everyone, and welcome to the start of a new year of CDAC webinars coming to you from the University of Illinois in Chicago. We're very pleased to welcome Zhou from the University of Texas at San Antonio as our seminar speaker today. Xuan is currently in the Department of Physics and Astronomy at UTSA. She received her bachelor's degree in materials physics with a minor in English from the Jiaotong University in China, and then a master's degree in mechanics and physics from the Technological University of Troyes in France. She stayed on there to complete her PhD in optics and nanotechnology. Xuan did two postdoctoral appointments at our sister university, the University of Illinois Urbana-Champaign, first in analytical chemistry, where she focused on mapping spatial distribution of plasmonic enhancements in photoelectrocatalysis. She also constructed a Raman microscope that coupled to a scanning electrochemical microscope. She then moved to another appointment in chemistry at UIUC with our academic partner, Dana Delott, who's on the seminar today. While working with Professor Delott, Xuan developed a high-speed hyperspectral imaging system for temperature and emissivity maps of individual explosive crystals and nanoparticles under shock compression with Professor Delott's tabletop shock apparatus. Professor Zhou's current research interests are in the areas of mechanochemistry and shockwave methods as applied to metal organic frameworks and energetic materials. She also uses high pressures to manipulate the optical properties of plasmonic nanostructures as plasmonic dye hybrid systems in the diamond anvil cell. Xuan has received the Outstanding Young Scientist Award by ACS Photonics at the Near Field Optics Conference and was also a finalist in the Science Image Challenge in the School of Chemical Sciences at UIUC. Today, she will discuss plasmonic propagation on a silver nanowire under high hydrostatic pressures within the broader context of the subject of her presentation today, entitled Plasmonic Hybrid Systems Under Extreme Conditions. Welcome, Professor Zhou.
Well, thank you, Steve, for the introduction, and thank you everybody for giving me the opportunity to present here in front of the high pressure community. So basically, just a slight little bit more about myself. Probably, if any of you or some of you have attended Dana's presentation, you probably are familiar with these two figures, let's say. On the left is about hyperspectral imaging of hot spotting explosives. On the right is the shockwave energy attenuation in a metal organic framework. So these works are done under shockwaves using the laser-driven flare plate apparatus in Dana's group at UIUC. So it was during this experience, actually, I was really, really impressed by how powerful high pressure and shockwave can be in terms of tuning the material properties. And thinking back about, our surface plasmon community, there was quite some significant problems to be solved and to remain unsolved. So that's why I was like thinking probably I need to apply the high pressure to nanophotonics and plasmonics, trying to see if there's any potential solution or to provide a deeper fundamental insights into the problems in the field. So just let me step back to introduce very briefly about what is a surface plasmon. Actually, it has two categories. One is called localized surface plasmons, and another is surface plasmon polaritons. Both are at the metal and dielectric interfaces. In the case of localized surface plasmons, we have a nanoparticle. Let's say a metal nanoparticle, usually gold or silver. And so if you have, say, light coming in, which we all know that light is oscillating electromagnetic fields, and let's now only consider about the electric field here. So there are a ton of free electrons, in the metal, right? So if you have electric field in this case, for example, pointing to the right direction, and your free electrons tend to move to the left, right? So in this case, and if, at a later time, if, the electric field swap its direction to the left, then the free electrons will, on the metal surface, will move to the right. So this, back and forth movement in response to the electric field, oscillating electric fields is called surface plasmons. So in the case of nanoparticles, since the oscillation has nowhere to go, and that's why it's called localized surface plasmons. And to characterize it, it has something called localized surface plasmon resonance. That means that is actually telling us the frequency or wavelengths of the excitation light that excites this collective charge oscillation most efficiently. So absorption, extinction, and scattering spectroscopies are all good ways to characterize the localized surface plasmon resonance. And in the case of plasmon polaritons, you need to have a metal surface or a waveguide, let's say a wire or something like that. Okay, similarly, well, in this case, let's step back very quickly about the electric field here on the nanoparticle, which is I forget to mention it very quickly. So in this case, actually, if you take a look at the local electric field that is generated by this, free electron oscillation. So you have negative charges on the right side, positive charges on the on the left side. So the electric field actually points from the positive to negative, in the dielectric, right? So in this case, if you take a closer look at this area, the electric field that is generated by the surface plasmons is in alignment or in the same direction with the external field. So in this case, it causes some optical enhancement in the very close vicinity of the nanoparticles. And this enhancement can reach to 10 or hundreds of times in intensity. So actually, that's actually is something very attractive for surface plasmons in terms of optical confinement because it happens only at the close vicinity of the nanoparticles or the metal surface. And also, it is very attractive because it enhances the local optical field. So in terms of the metal surface, we have similar cases. Let's say electric field shines at the metal, and then you have the free electrons tends to be moved to the left side in this case, and then leaving the positive charges on the right. And this positive charges will cause some disturbance on the material around it, so that it attracts negative charges, the free electrons towards it, and then leaving positive charges here. And then the disturbance just propagates since it is a whole piece of metal surface, right? And if it comes to a later time when the electric field points swap its direction, then the electrons will also change its direction. So in this case, it's like as the metal surface is exposed under oscillating electric fields, this electron charge is going to oscillate as well and also propagates along the surface. So typically we have gold and silver that are most frequently used plasmonic materials. But since a decade ago, people have been, looking at different materials for surface plasmons, and they all find that, doped semiconductors, including oxides and sulfides also, that can also support surface plasmons. It's just like a matter of, which frequency or which wavelength it is. So gold and silver support surface plasmon in the visible range, and sometimes gold supports in the near IR. But oxides supports the surface plasmons in the IR or far IR here in this case. Okay. So talking about how impressive they are. So of course we have to mention about the applications, and I think the most sophisticated applications of surface plasmons should be the photocatalysis and optical sensing, and they are all based on nanoparticles or surfaces here. And in this figure, it just shows the photocatalysis on a silver surface that is for carbon dioxide reduction. And on the right side, we have the optical sensing that is based on either surface-enhanced Raman scattering or surface-enhanced photoluminescence. So these are all based on nanoparticles, let's say plasmonic effect of the nanoparticles. And also there are something very attractive called cancer therapy, based on the plasmonic thermal effects of the nanoparticles, of the plasmonic nanoparticles. So when you shine the light, the electron charge oscillates, and then this actually, creates the elevated temperature around the nanoparticles. And if this nanoparticle is around a tumor cell, it just burns the cell. And this is how they, do with surface plasmons for the cancer therapy. And in the case of propagating surface plasmons or surface plasmon polaritons, the application could be directed nanolasing or photonic integrated circuits. So in these two cases, it requires the plasmonic surface, and in the nanolasing case, it's actually having a favorable interferometer, and this semiconducting nanowire is being excited and emit light. And then there is a spacer between the semiconductor and this plasmonic surface. And this way, it just traps the light actually within this tiny little spacer. And this way, it's like more confined and well directed. And for the photonic integrated circuits, it's in the case of plasmonic applications, it's more about plasmonic waveguides. And this has really great promising applications in optical quantum computing and data transfer and storage in that and communication as well. So in terms of plasmonic waveguides, of course, actually there is some big problem hidden behind it, and that are the losses actually. So we have been using silver nanowire as a typical, very typical plasmonic waveguide, and it is the most well-studied plasmonic waveguide. And say, for example, if you couple light into this end, you're expecting the surface plasmon to propagate along the silver nanowire and eventually have the light coming out. So it sounds really promising because it is like your really highly confined light and enhanced optical intensity in the near field. However, it suffers from the significant loss that is caused by multiple reasons. One is actually green boundaries, and another is surface roughness. And something related to the intrinsic property is the internal damping. So in terms of green boundaries and surface roughness, it tells us if the electron oscillation just travels across the green boundary, or it travels at the surface and it has a rough surface on the metal. So in this case, it causes some losses. And in terms of internal damping, we have two major categories. One is electron phonon coupling. That is when the electron is excited by the surface plasma, by the external light, and it just travels and then meets the lattice vibration that just gives the energy to the lattice vibration and that is something called the electron phonon coupling in this case. And then we have electron scattering, because there is a sea of free electrons in the metal surface or in the metal, but not all the electrons were really excited by by the light and generate surface plasmons. So there are something we call hot electrons and cold electrons. So when hot electrons are oscillating and transporting, the plasmonic vibration, and then when it meets the cold electrons, it tends to, give its energy to the cold electrons, of course. And these two are also some intrinsic property of the material, and which is just hard to mitigate under ambient condition. But for the green boundary and surface roughness, you can always improve it or mitigate their impacts by, let's say, improving the chemical synthesizing methods or improving the nanofabrication technique. So that's why this problem is just like remaining there in the field. And so when I started my independent research, I was like, okay, so let's try to tune, the these intrinsic properties of the material using high pressures and see what will happen. Because I did a kind of literature research and trying to pick all plasmonic materials in the slides and then see how high pressure can, affect these intrinsic property of the plasmonic materials. And first of all, we have lattice compression. In case of gold and silver nanoparticles, we're expecting quite some, volume change and high pressures. And in terms of in this case, we have van der Waals material that is graphene here. It's also a plasmonic material. And under high pressures, the material structure will change by, creating a interlayer bonding. And in terms of phonon frequency, in this case, also gold, silver, aluminum are all plasmonic materials. And we can see that the phonon vibration just shifts to a higher frequency. And as a result, actually, the electron phonon coupling just drop, significantly under high pressures. And as we mentioned, electron phonon coupling is actually one of the major loss mechanism actually in the surface plasmons. And also when it comes to the electron density of states at the Fermi energy level, and we have been seeing that there is a constant drop of the DOS here as well under high pressures for gold and silver here. Okay, so just let's take a look at what happened, to the metals nanostructures under high pressures. And previously, there was actually only about 20 to 30 papers published in this field about the metal nanostructures on high pressures. And I just picked two of the most representative ones. On the left side, we have the authors working on gold nanospheres, and they were detecting the localized surface plasmon resonance as a function of the pressure. And in this figure, they plot the localized surface plasmon resonance as a function of the high pressure here. And they saw first a redshift that is attributed to the increased medium refractive index. And then above 10 gigapascals, they started to see an increased charge density kicking in and causes a blue shift of the localized surface plasmon resonance. And of course, there's something called a refractive index that is also affected, and that is also playing a very important role in the localized surface plasmon resonance here. And we can see from here. But in terms of increased charge density, this is how it is affecting the energy or the frequency and wavelengths of the plasmon resonance. It's so here omega p is the bulk plasmon frequency, and here n is the carrier density. So if you have the carrier density increased, you're expecting an increased frequency and therefore a blue shift in the spectrum. So on the right side, we have another group working on gold nanoclusters that is 1 to 3 nanometers. In this case, it's not localized surface plasmons, nothing related to plasmons, but at this size, gold clusters work similar as a dye molecule. They emit light. So in this case, the authors have seen first increased photoluminescence intensity, and until 2.3 gigapascals, they start to see a decrease of the photoluminescence intensity. So these works are done with gold nanostructures under high pressures. But in our case, if we're interested in propagating surface plasmons, we picked the silver because, as I mentioned, silver was the most well-studied plasmonic waveguide at ambient. So for the silver that we used, we had a diameter of 120 nanometers and the length of 10 to 15 micrometers. And these silver nanowires were wrapped in a thin layer of PVP. And we need that thin layer just because we want to create a tiny little spacer between our plasmonic structure, and later on I will introduce our probe molecules so that we can avoid fluorescence quenching. So on the left side, it is a dark field image of the silver nanowire. Here's a TEM and image, and there is a spacer here, PVP spacer. And also on the right side shows UV-vis spectroscopy on the silver nanowires. And it has a typical peak around 370-80s here. And then here, this line at 532 marks our excitation wavelengths in our experiment. So here is my experimental setup. Excuse me. So at the bottom left, we have a photo of the experimental setup. All optics are actually shielded in the box, and we have inverted microscope. On the left, we have like a spectrograph coupled to a CCD. And we put the diamond angle cell, which is really a simplified version of the cell, but it's good enough for us to use. And we put it on the sample stage, and this is a top view of our cell, actually. I'm not going to introduce anything about the high pressure cell because everybody knows it, I believe. But just inside the cell, we loaded the plasmonic waveguides, which are now wires, as you can see in this image here and there, hair thing, like wires here. And then we also use a pressurizing medium. We call it a mixture of methanol, ethanol, and water in the ratio of 16:3:1. And this allows us to create a hydrostatic pressure around 10 gigapascals, up to 10 gigapascals. And inside the solvents, we dissolved some dye molecules, which is rhodamine 6G molecules, as actually a probe to tell us where are the surface plasmons, right? So we shine a laser of 532 nanometers and focus the bind objective to the plasmonic waveguide, and it will excite some surface plasmons. And as surface plasmon propagates, the plasmonic will just like interact with dye molecules and will cause the fluorescence of the dye molecules, even if the dye is away from the laser excitation. So we collect the fluorescence of the dye molecules, and after filtering by the dichroic beam splitter and long pass filter, and then collect the fluorescence image. Actually, this is an actual image of a nanowire and when we shine at one end of the wire. So you see that the surface plasmon propagates along the nanowire here. And in this slide, I'm just showing a comparison of the plasmon propagation on a silver nanowire at low pressure when the cell was just closed, and also at a higher pressure that was 6 gigapascals. So in this case, as I mentioned, plasmons were probed with fluorescence of rhodamine 6G molecules. All light emission that you were seeing was the emission from the dye. So this experiment was carried out in room temperature. There was no temperature effects that we have been, so things are pretty simple, only pressure effects here. And as you can see that we have seen a significantly longer propagation distance under high pressures, and we tried to quantify that. So we did a cross-section profile along the nanowire to tell us what is the intensity as a function of the distance from the center of this laser spot. And this figure plots the profile, intensity profile. So I would say stress here, don't really care about the intensity here, because we had to adjust the intensity as we increase the pressure, because the fluorescence of the dye just get quenched a lot by the high pressure. But what we really care is this L here, that is the plasmonic propagation distance. And here I sub 0 is the intensity that we detected at the background here, because it may have some scattering inside the cell and contributing to some intensity on the background. And here Max is the maximum intensity, that is the at the laser spot center. So by plotting this, we call it, we were able to determine what is the propagation distance. Okay, so on the left side, we have this under ambient when the cell was just closed under lower pressure, we have the propagation distance at about 1.28 micrometers. And on the right side, when the pressure was increased to 6 gigapascals, we see that the propagation distance was doubled. So, well, this is really promising, but since we have dye molecules, imagine we have dye molecules everywhere inside this cell. So it is just like really a complicated system. So just by probing the surface plasmons, this probing activity itself is actually causing some loss because you need the energy to be transferred from the surface plasmons to the dye, right? So in this case, we thought about something, a improved configuration of this experiment. So we trap the dye molecules inside the photopolymer. And in this case, we find some structure here and we created a tiny little polymer bridge doped with dye molecules. So in this case, we don't have dye molecules everywhere, but they are all trapped in this photopolymer. So this is how it looks like under our microscope. As you can see, SEM image is actually for sure telling us more details about how the bridge looks like. And this actually is our laser spot, and it is pretty big as compared to the size of the nanowire. And I have to say that the bottom of this tiny little polymer bridge is probably affected by the laser spot. So just use that one as a reference. However, the top, parts of this bridge is outside the laser spot. So when it lights up, it tells us, yeah, the surface plasma is there. So as different pressures, as we can see, there is higher, well, as pressure increases, this top part of the bridge just lights up at 2 gigapascals and then decreases at 5, and just like we cannot see it anymore at about 8 gigapascals. So this actually tells us there might be an optimized pressure in the system, and that means there are multiple processes that are probably competing with each other. And these are just experiments, and we have been trying to find theorists for a long time to do the calculation for us. And eventually, I was really, really lucky to have Dr. Oleg Pretzel to work on this with me. And while we're waiting for his DFT simulation calculation, let me just bring one of his paper here. Just let's take a glimpse of, at what might happen under high pressures that may affect the surface plasmon propagations. First of all, of course, we're really interested in the electron-phonon interactions. So just by reading this table here, this figure here, at 6 gigapascals, we find that the electron-phonon interaction was reduced by about over 20%. So this is a very, very, very big drop, actually, when you consider about plasmonic losses caused by this electron-phonon interactions. And now let's take a look at electron-electron interactions. So the first thing we need to consider is the volume reduction, of course. And so let's say about the volume decrease of the cells of the gold and silver. In this case, at 6 gigapascals, by reading this figure, we estimate about 5% drop of the size of the cell of the silver. So if you think, so decrease the total volume, that might cause an increased charge density, but it's probably not that simple, because when you consider about the total number of electrons that are available at the Fermi energy level, they actually drop under high pressures. So I have to say, that electron-electron interaction might be really, really complicated in this case. And we do need DFT simulation calculation on this to tell us, what's how much they really contribute and what is eventual, electron-electron interaction that is contributing to the surface plasmon propagation in our case. So that's let me just bring our attention a little bit to the probe molecules itself, because that has been bothered us for quite some time. Because when we increase the pressure, we see a significant drop of the fluorescence signal under high pressures. But we need those dye molecules to still work as a probe in the diamond envelope cell, which is sealed, not allowing us to carry out any scanning probe microscope measurements for the surface plasmon propagation. So that is why we have been really studying how dye molecules may behave under high pressures. I know that there are quite some research, focusing on the rhodamine-63 molecules under high pressures, but probably not at this concentration, not at this high pressure indeed. So in our case is like we take a look at the dye molecules in methanol and ethanol water, and we have the absorption spectrum shown on the left, and we have the fluorescence spectrum shown on the right. Again, the laser was at 532 nanometers to excite the emission. So we have seen that from the absorption spectrum, we have identified two peaks. One is the monomer peak, absorption peak, and that around 535 nanometers, and we also have the H aggregates absorption peak around 500 nanometers. By saying H aggregates, that means the dye molecules are stacked face to face, and perfect H aggregates do not emit light. And also we see an overall peak shift to the red. And also we have, this redshift of the absorption actually indicates the reduced energy gap between HOMO and LUMO energy levels. And also you have the relative intensity reduced for H aggregates over monomer. And that indicates a increased ratio of H aggregates over monomer in the solution. And in the case of fluorescence, we have the reduced fluorescence intensity overall, and also a very complicated peak shift. You can identify here that is a red shift first at lower pressures, and then as pressure keeps increasing, it became blue shift here. And also, we were trying to see if different solvents will give us different results. It seems yes, because from the fluorescence spectrum of the rhodamine-63 in IPA, we have seen that there is a reduced relative absorption of the H aggregates over monomer, actually. And also monomer also sees a constant redshift in this case. And in the case of fluorescence of rhodamine-63 in IPA, we have seen that there's a reduced intensity. And also, please note that there is a change on the incident power by applying OD filter, but for same OD filters, we have same incident power. In this case, if you compare the same OD filters, then emission signal collected with same OD filters, then that means it's actually still a constant drop of the intensity. And also we see a constant redshift, and which is also the HOMO-LUMO gap reduced by the high pressures. So this is not really obvious here, but when we do a peak normalized, let's say, fluorescence intensity here, we actually see some tiny little feature here around 700 nanometer for the rhodamine-63 in methanol ethanol water. So we have been trying to wonder why is that, and this looks like it's probably the emission from the aggregates that were not perfectly aligned. So that means when the aggregates were not perfectly aligned for H aggregates, they can still emit light. And this combined with absorption spectrum, we believe that this is emitting emissive H aggregates. So when we bring it to a higher pressure, just to confirm us our guess, we just introduce we just have the study carried out under a higher concentration of the dye, and this is no longer a shoulder, but it's just like becoming a dominant peak actually here for the aggregates emission. So but also in this case, if you consider about higher concentration of dye molecules in IPA, this peak does not pop up, and at lower concentrations we do not see this. So that means this peak is from aggregates, and also it's solvent dependent. And when we consider about the it's like you don't have this peak here, but it does not mean that IPA does not form aggregates. Actually, IPA, rhodamine 6G solubility in IPA is much, much lower as compared to methanol, ethanol, water. In the case of IPA, it is about 20 grams per liter. And in the case of methanol, ethanol, water, it is about 300 grams per liter. And so that's actually, if you consider about the absorption, that is similar to monomer in IPA, but emission is significantly redshift, and it is redshifted, and it is similar to aggregates. So by combining this information, we believe that the rhodamine 6G actually forms excimers in IPA. By saying excimers, it is actually the short for excited dimer. So it only forms at excited states, and only one molecule of the dimer absorbs. That's why the absorption looks like a monomer, but the emission reads like aggregates. So that's why it's so significantly redshifted. And here this table just summarizes the peak shift. Actually, we performed measurements also in a third solvent, that is methanol, but they read almost identical to methanol, ethanol, water. So I'm just not going to provide every single data to make the slides more crowded. But here, this peak just summarizes how the peak shifts, as a function of the pressure. So in the case of methanol and ethanol water, so we always see a red shift, then a blue shift, and then a red shift as a function of pressure, and similar to higher concentrations. But in the case of IPA, we see similar red shift, blue shift, and red shift at lowest concentration. But when the concentration increases, we just see almost a constant red shift. And also here, this part just plots the redshift of the secondary emission peak. And this just by combining the fact that this blue shift is also, as we mentioned, it's like the red shift is due to the homoluminal gap reduce the homoluminal gap of the molecule. But this blue shift, we think it's because of the interaction between the dye molecule and the solvents. So because this blue shift, the existence of this blue shift actually is affected by which type of the solvent you're using, and also how concentrated your molecule is. So that indicates is solute-solvent interaction. So that comes to my conclusion here. Actually, we studied the silver and dihybrid structures at high pressures, and we also observed a longer propagation distance and a lower loss of the surface plasmons at high pressures. And it seems that there is an optimized pressure exists with lowest losses. And we believe that this could be resulted mainly from the pressure modified electron-electron scattering and electron phonon interactions. And to quantify the contribution of them, we need a DFT calculation, and it is on the way. Please be patient. And also we have studied, tried to analyze how our probe dye molecules were affected by the high pressure. It seems that yes and no. It has no effect on how we interpret our plasma propagation data, because our emission intensity from we're just relying on the emission intensity from rhodamium 6G, not actually the selected wavelengths. But it actually causes some problems to us because the reduced absorbance of the dye at high pressure makes the surface plasmon surface plasmon polyton really hard to show up, and it's even when they're there. And also, the reduced emission requires us to keep adjusting the laser intensity, which is also something of a problem there. And so that's why we're thinking about at this moment looking for plasmonic probes that are not too sensitive to high pressures. And we have been thinking about NV centers for a while. And also, we need to discuss about that more in detail with Ross and Steve, maybe. And also, we have the ongoing work focusing on other polytonics. That's by saying that we mean phonon polyton and exciton polyton. That is similar to surface plasmon polytons. They are just phonon vibration and exciton vibration that is propagating along the surface. And also, we are interested in looking at hydrides of the materials that can support surface plasmons to find better chance of plasmon propagation. And that is all what I want to talk for my current research. And here, this is a photo of my group, and the work is mainly done by Kate Johnson, my graduate student, and also with the help of undergrad students, Kenneth Mikolajczyk. And also, I would like to thank my collaborators from Argonne National Lab guys, Dr. Gary Witterit, Dr. David Kostola, and Dr. Richard Schaller for helping us with analyzing the dye molecules. And also, Dr. Oleg Prezvo is working on the DFT computation work here for us to, analyze the electron-electron scattering, electron-phonon interaction, quantify those things. And Dr. Olivia Sobera is providing us the photopolymers that we created. And with that, I would like to say thank you and then ready to take any questions.
Well, thanks very much, Zhou, for your guiding us through these challenging experiments. If there are any questions, you can either raise your hand or you can type your question in the chat. I guess I'd like to ask one question about maybe you could say a little bit about your sample preparation, how you set up. It seems like your experiments are going to be really sensitive to the way the samples are prepared.
Yeah, so the silver nanowires we purchased from Sigma Aldrich, and we came here, we rinsed it for a couple times, just to replace the solvents. And then also after that, we mixed it with a solvent of rhodamine 6G molecules that were also in methanol ethanol water in this case. And then by specific ratio, my students, worked a little bit on trying to find the proper ratio so that we don't have too many nanovirus in a cell. And then it's actually just as a suspension inside the in the methanol ethanol water solvent. And then we just pick a tiny little portion and then just load it in the chamber, the hole of the gaskets. Yeah.
Right.
Yeah.
So about the nanoparticles. So are you looking for a certain number that you have in there in the cell or a certain concentration?
In the case of nanowires, we're looking at single nanowire. because we're actually just tracing how far the surface plasma propagates on a single nanowire. If it comes to a bundle, then things will be more complicated. Yeah,
Right.
just because the surface plasma will, I mean, two nanowires, there will be a tiny little gap in between, and then it actually causes some extra enhancement there. I mean, it might be a good experiment, but it's like just at this moment, at this stage, is just like uh going to complicate things more.
Yeah. Um, I was wondering about the sort of how your solutions of your uh, dye molecules will behave with pressure. Um, are they are they liquid throughout the pressure range, or do they solidify at some pressure?
Well, yeah, in this, let me check if I can. Yeah, so in this range, let's see. For IPA, well, IPA, I don't remember that we see any solidification or crystallization in IPA, obviously, just by looking at the eyepiece. But according to literature, I know that the hydrostatic, limits for IPA is around 4. Um, but we just go high enough to see, just like go beyond that limit just to see what are the impacts it might have. Yeah, but we don't. In the case of IPA, we don't see it. In the case of mule, we don't see it. But in methanol, yes, we do. We do see the crystallization of the medium at some points, and that is usually when we start our just stop our experiments. Yeah.
Yeah. Okay. Alec, please go ahead.
Yeah, thanks. You actually kind of sort of answered my question. 'Cause I was going to ask basically if there were any interface effects, because it's, I'd expect if it's a high frequency device and you have two materials of different dielectric functions next to each other, there might be something going on. But I do know for some methanol ethanol mixtures, there might be something weird going on above 4 GPa in the with the dielectric properties. I would have to dig up the papers, but I seem to remember reading that. I was just sort of wondering, and again, you kind of addressed this. Have you
Um,
sort of taken into account just changing dielectric properties of a medium or as opposed to a vacuum, not necessarily just so it's just like an interface maybe.
we're talking about this one here, the dielectric function, of course. I mean, it's reflected by the refractive index here.
Yeah, you get a measure of it there, but the
Um,
interface,
yeah,
the
yeah,
interface, 'cause typically a plasmon, or usually it's my understanding most of these are done either in a vacuum or in a inert, not surrounded by a solid.
yeah. Oh, no,
So I was almost wondering if there could be any higher order effects or any higher order coupling going on.
um, not really sure at this moment, but I mean, if it is still in liquid, it should be still fine. It's like just when with a higher refractive index or a modified the real part of the dielectric constant.
Yeah,
It's actually what we're expecting with the higher index. That means the propagation distance usually gets reduced. Um,
yeah,
so we're actually fighting against this effect to have a longer propagation distance. Yes, if we can change the let's say the pressurizing medium to something that is not going to have such a sensitive effect as as a function of pressure, that would be really, really of a great help. Yeah.
yeah. Okay. Because I seem to remember there was some proposal for a liquid-liquid transition in methanol, ethanol, water around like 4 GPa.
Yeah. Okay.
And that sort of corresponds to your the change of that feature you see.
I have a question. Excuse me, I have a question.
Go ahead, Dana.
Um, yeah, can you think about making an analogy between plasmon transport and superconductors? So in a superconductor, right, you have an electron-phonon interaction so that the electrons get into phase with the phonons and they don't get scattered. Now, superconductivity is really different because the electrons last forever, but the plasmons have a short, have a lifetime. But is there some way of, engineering a system where you really can find a condition that minimizes the electron plasmon scattering?
Well, in our experiments, we're trying to look into this, just like having the high pressure compression and then try to modify the electron phonon coupling. But of course, if you're talking about superconductivity, yeah, that's why we're thinking about probably, also talking to Ross and Steve about the hydrides, right? So take a look at, if there's any chance that we use superconductors to carry surface plasmons. In this case, we're not expecting, significant losses as introduced by electron phonon coupling, right?
Well, in the hydrides, what happens is you create a new set of phonons that are extremely high frequency. Okay, so high frequency that they're like near resonant with the conduction band. Okay, and then that really reduces the scattering. But maybe you should try to think, it would be possible to try to think about this the other way, which is rather than trying to tune these things, try to figure out theoretically what kind of electron phonon interaction you would need in these materials to reduce. I mean, I guess what I'm trying to say is there a possible way where you can totally minimize the plasmon phonon scattering? You can't do other things. You can't make it, conduct forever or, have a mean free path longer than the lifetime. But maybe there's a way of engineering it so that you really reduce the plasmon phonon scattering, either through composition or pressure or temperature.
Yeah. Well, but that is probably the point of what we do the research for, right? So trying to, see if it is possible to apply, extreme conditions so that we can, change this there to have a longer propagation distance.
Yeah, my criticism is that you're sort of hoping for a miracle. Right, it's like, oh, maybe I'll find the right system accidentally that'll do this, rather than kind of coming at it from both ends. Because, what should it really look like to minimize or eliminate the plasmon phonon scattering? That would be a really big deal, not just for transport, but for catalysis.
For everything, right?
Right, because you get much more hot electron transport. Okay, well, you can't do it while I'm talking to you, but
hopefully there will be a way. We'll see. I'll talk to Oleg to see if it's possible. He is running theory for us, and then about shifting phonon frequencies a lot. But so far, high pressure seems that it's doing something there. But if the pressure is high, not high enough, what will happen? I don't know at this moment. Yeah.
okay. Well, thank you very much. Really interesting.
Thank you.
Okay, well, thank you for your questions. Thanks everyone for attending. If there's no more questions for Professor Zhou, then please join me in thanking her for a really nice talk. There's lots to do, and we'll be looking forward to seeing how it all evolves out. We hope we can collaborate, and we'll look forward to seeing you up here in Chicago the next time you come to Argonne.
Sure. You'll let you know.
Okay. Thanks so much, Zhou.
Thank you. Bye. Have a nice day.
Okay, you too. Take care.